Bismillahirrahmanirrahim. New topic: two-port networks. Chapter 18 in William Height. Chapter number 18, William Height, and this one is the last topic for our course. Two-port networks. Before going to two-port networks, let's discuss some basic concept, basic things which are helpful in solving two-port networks. So first we discuss. You have heard many times that VDR, that is voltage division rule. So voltage division rule is applied where voltage divides actually. Voltage divides in series circuit. For example, this one is voltage source, this one is resistance, this one is resistance, and this forms a closed path. This one is source voltage, this one is resistance R1, this one is resistance R2, current is flowing in the loop. So across this across this voltage drop is V1 across this resistor, and across these terminals the voltage drop is V2 because resistance R1 gives voltage drop V1, resistance R2 gives voltage drop V2. So voltage division rule, if you want to calculate voltage across R1, that is V1, is equals to total voltage multiplied by same resistance over sum of resistance, that is equivalent. We know very well the resistance equivalent of two resistance in series connections are nothing but the sum of these two. This is equivalent resistance. So if we generalize this formula, for example, there are nth branches. There are nth branches connected to this source. How we calculate the voltage of the and vice versa. See, V2 is equals to total voltage V times R2 over R1 plus of R2, right? If there are nth branches, that is there are R1, R2, R3, R4 till nth, n is general number, right? Then we have some general formula for that. For example, we want to calculate the nth branch voltage Vn, for example. The formula, generalized formula for that is total V multiplied by nth branch resistance, that is Rn, divided by R equivalent. So this becomes a general formula for voltage division rule. I hope you understand. Now current division rule, again we have to draw a circuit, parallel circuit, because current divides in parallel. Before we drive voltage division rule, voltage divides in series. So this is parallel. So let's suppose there are two branches, R1, R2, and source voltage V. The current goes in first branch is termed as I1. The current goes in second branch is termed as I2. The current comes from the battery is total current I. And it is obvious that the total current, that is I, is nothing but the sum of branch current, that is I1 plus of I2. Or either you apply nodal analysis, if you apply Kirchhoff current law, the current entering is equals to current leaving. So current entering is equals to current leaving, Kirchhoff current law. Okay. So in current division rule, if we want to calculate the current of I1, that is this branch current, that is I1. So it is nothing but is equals to I1 total. I1 is equals to total current. In voltage division, it was total voltage. In current division, it is total current actually. This I current, total current, multiplied by. Now in current division, the resistance in voltage division, the resistance was same. That is, if left hand side was V1, the resistance was R1. If left hand side was V2, the resistance was R2. Here, the resistance is otherwise. That is, if the branch one current, we want to calculate branch one current, the resistance is otherwise. Otherwise, resistance is R2. So here is R2 divided by R1 plus of R2. This is current division. The I1 current is equals to total current multiplied by otherwise resistance divided by sum of these two. Similarly, I2 current is equals to total current multiplied by R1. See, I1 R2, I2 R1 divided by R1 plus of R2. This is okay. Again, we want to generalize this formula. Generalize this formula for the nth branch current. Before that, we must know what is the general formula for current division. The general formula for the current division equals actually, see, I1 equals total current multiply by equivalent resistance over the resistance of that branch which we want to calculate the current, that is R1. How we obtain this formula? Come up. Okay, what is the equivalent for two parallel resistance branch? What is the equivalent? R1 R2 R1 plus of R2. This is the equivalent for the two branch, that is two branch equivalent parallel resistance equivalent, right? Two branch parallel. So when I1, we want to calculate I1 total current I multiply by equivalent, right? So put equivalent divided by R1 divided by R1. So R1 is cancels with R1. R1 is cancels with R1. What is I1? What is I1? The same which we have wrote earlier. The same, that is total current times R2 R1 plus of R2. We wrote earlier, right? This current. So from this, it is concluded that the nth branch current, for example, there are several branches. R3, R4, R5 till Rn. That is nth branch resistance. So nth branch current is equals to total current. See the standard formula: total current multiply by equivalent resistance. So multiply by equivalent resistance divided by, if the branch is 1, then it was divided by 1. If the branch is n, it is divided by the Rn, right? Nth branch resistance. So this is, remember this general formula for the current division. Whether two branches, whether three branches, whether four branches, this formula is valid for, general formula valid for nth branches resistance currents. I hope you understand. Okay, two port networks. What is mean by port? Port means pair of terminals, right? Pair of terminals. If there is one pair of terminal, for example, this one, and a passive element, that is inductor, is connected, or maybe capacitor, or maybe resistor, whatsoever. But this is pair of terminals. So this is one port terminal. So this is one port terminal. Now, two port terminal. Okay, two port terminal. For example, this one is network, and these are the terminals. See, two ports, pair of terminals, pair of terminals, pair of terminals. Input pair terminal, output pair terminal. Incoming, outgoing. So you can take the example of transformer, primary side, secondary side. Take the example of transistor, primary side, that is transistor input and transistor output, or op amp, or any other device, that is multi ports. Basically, this is two port network: incoming, outgoing, input current, output current, input voltage, output voltage. So in two port networks, we have to calculate certain parameters, and first parameter is impedance parameter. The first parameter is impedance parameter. We know very well impedance is designated by Z. It is denoted by Z. Impedance is what? Ratio of voltage over current. What is impedance? Impedance is ratio of voltage over current, right? Because we know that voltage equals to current times impedance. So impedance equals to voltage over current. So let's start from impedance parameters, and by considering a network, a generally two-port network, so we can consider like this. For example, we have a network that is voltage source. Actually, we have to connect a voltage source across it, right? Okay, first we draw the general circuit. So generalized, we may say that linear network means a network that the passive elements connected, maybe resistance, inductance, or capacitance, whatsoever are connected at input terminals and connected at output terminals, and they may be connected through a voltage source driving a current that is I1, and also a voltage source that is V2 driving driving current is I2, or they may be connected through current source. The voltage drop is V1 across input terminals. The voltage drop is V2 across output terminals. So this is a generalized form of two-port networks. So so we can write the equations for the impedance network, that is V1 equals Z11. I will explain this. Z11 times I1 plus Z12 times I2, and V2 equals Z21 times I1 plus Z22 times I2, or we can form them in we can formalize like in matrix form. V1 V2 equals Z11 Z12 Z21 Z22, current I1 I2, and if this whole matrix is Z, then we may write like is equals to Z impedance over current I1 I2. Okay, so here we must define what is Z11. Z11 is open circuit input impedance. It's open circuit input impedance. Z12 open circuit transfer impedance from port 1 to port 2. Transfer Open circuit impedance transfer impedance from port 1 to 2, from port 1 to 2. See, from port 1 to port 2. And what is Z21? Z21. Z21 is again open circuit transfer impedance from port 2 to port 1. From port 2 to. And what is Z22? Z22. Z22 open circuit output impedance. It is nothing but open circuit output impedance. Open circuit output impedance, open circuit input impedance. In between that, transfer impedance. That means that impedance which is common at both the ports. At both the ports, right? I will we'll draw a problem also. You will better understand that problem. Okay, now we have to find the impedance parameters. For that, we need to open circuit output impedance. That, for example, we can draw the circuit, that is this one, voltage source. It draw a current, and there is a network. There is network, and the output terminals, that is the current. What is current? If the terminals are open circuit, what is the current? Current is zero because impedance is infinite. In open circuit, current remains zero, voltage remains maximum. In open circuit, impedance becomes infinity. So resistance, the current is zero. So this is I2 is equals to zero, and output terminals are open circuit. Output terminals are the means port 2 terminals are open circuited. So when they are open circuited, what is Z12 and Z21? We write all the parameters, that is Z11. Okay, this is V1, this is current I1. Okay, so the values of the parameters can be evaluated by in this case I2 is 0, so Z11, that is input impedance, is what? Input voltage over input current, termed as I2 equals 0. I2 equals 0. And what is Z12? Z12 is voltage V1 over current, the ratio of voltage over the input voltage and the output current. At this condition, letting I1 is equal to 0. That is, this the terminal is being open circuit in this case, because I1 equals 0. What is Z21? Z21 equals V2 over I1. Again, I2 is equals to 0. This condition is a ratio of secondary voltage, the port 2 voltage over port 1 current, and Z22 equals V2 over I2, because it is purely second port Z22. So in this condition, I1 equals 0. See, in all four cases, I2 equals 0, I2 equals to 0 when we are calculating the impedance of port 1. I1 being 0 when we are calculating the port 2 impedance, right? So remember this. So you can see in this that is when terminal 2 is open circuit, but the voltage appears over it, right? V2 is appears, but I2 0, because it is open circuit. So the parameters are right, Z11, Z21. Okay. In both the denominator, the current I1 appears, because I1 flows actually, not I2. I2 is 0. In both the impedance parameters, see the ratio, I1 current appears, I1 current exists, right? In the second circuit, input terminals being open, that is these terminals are open, so the current being 0, but the output current flows, that is I2 flows. So see the impedance parameters Z12, Z22, in the denominator I2 appears. See, in both the denominators the current I2 appears. So it is like this. I hope you understand. So according to the network, to obtain Z21, and to obtain Z11 and Z11 and Z21, we consider a voltage source, that is V1, and current source, the current, that is I1, to port 1 with port 2 open circuited, right? I have already did. So Z11 equals, no need to write again, let go. So what basically is that impedance Z11 and Z22 are called driving point impedances, while Z21 and Z22 are called transfer impedances. If we connect voltage source across input terminals, and we connect emitter on output terminals, and we read the emitters read the same current value as it is connected on input terminals. So that's why reciprocal two port network. That means source connected on one side gives the response, that is current. When source connected on the other side, it will give response the current, that is same. This emitter and this emitter reads the same value current. So note that when the two port network is linear and has no dependent sources, the transfer impedances are equal. Transfer impedances, that is Z12 equals Z21. But remember this condition for when the network is linear and no dependent sources are connected, right? So the two port is said to be as reciprocal two port network. So this means that if the points of the excitation and responses are interchanged, point of excitation and responses are interchanged. See, point of excitation and response, point of excitation and response. So when they are interchanged, so when they are interchanged, the impedances, the transfer impedances remains the same. The transfer impedances remains the same. So we can equate Z12 equals to Z21. The transfer impedances remains the same. So in that condition, we reciprocal network yields that V equals Z12 times I, that is excitation and response being same. So we may write V equals Z21 I, again excitation and response being same. So we may write like this when connected. So we this is only possible when, okay, this is only possible when Z12 equals Z21. That is both the transfer impedances being same. Any two port that is made entirely of resistors, capacitors, and inductors must be reciprocal. Remember. I hope you understand. So in two port networks, we can write T equivalent, which can be used if the network is not reciprocal. If the network is not reciprocal, its T equivalent maybe it will be represented by T equivalent. If the network is not reciprocal, a more general equivalent network is can be shown like this. More T equivalent. You know what the T is. This is the T. T equivalent. So Z11, Z11 minus of Z12, the current that is I1, the voltage that is V1, and this one is Z12, Z12 between port 1 and 2, common impedance. Z12, 1, 2, port 1 and 2. And this one is Z22 minus Z12. The current is I2 and the voltage is V2. Is equivalent T representation. If the network is not reciprocal, then they may be changed with the dependent sources. They may be changed with the dependent. So if the network is not reciprocal, this may be because this one is Z11 input side, input terminal. That is, this one carries I1, and here it is a dependent source. We know that dependent source is shown in diamond shape. Dependent source is shown in diamond shape. Here again the dependent source that is shown in diamond shape, and we give the polarity of this dependent source, and this one is Z12 times I2 because its impedance referred to this side, and this one is Z21 times I1 because I1 referred to this side, referred to that side. Polarities plus minus, impedance of this side Z22, the current I2, and the voltage V2. Same is the case here. The voltage V1. The voltage V1. So V1, I1. Okay. And if the network is not, oh sorry, join this also. No. If the network is not the reciprocal, so the dependent source shows the corresponding the according value. Right. I hope you understand. Let's do an example. Determine the impedance, that is Z11, Z21 in the network. That is problem. Determine impedance Z11 and Z21. So determine Z parameters. Actually, you have to find Z parameters. So draw the network. The network shows the resistance, this network, and we have 20 ohms, 40 ohms, 30 ohms. The voltage, this is input, this is output. So to determine the impedance parameters, you have to find the impedance parameters. What they are: Z11, Z21, Z22, and Z12. Okay, all four parameters, all four parameters of impedance. So we apply V1, that is we apply voltage V1 and letting our current to the input and leave the output open circuit. We leave our output open circuit. So it is obvious that when it is open circuit, the current, there is no current, right? It remains open circuit. Apply voltage V1, test voltage source on primary side. So what is the impedance? That is Z11. The impedance is nothing but the ratio of voltage over current. Voltage over current. This current is I1. Since this there is no this side is open circuit, no current goes here. This whole current flows from 20 and 40. So 20 and 40 are in series connection because same current flows. So what is V1? V1 is 20 plus of 40 times I1 over I1. I1 is cancelled with I1. So is equals to how much? 60 ohms. The first parameter Z11, 60 ohms. Similarly, what is Z21? Z21, recall formula, that is, it was ratio of V2 over I1. So what is V2 in this case? This is open circuit, but remember voltage appears, right? This remains open circuit, but voltage, what voltage appears over here? The same voltage which drops across 40 ohm resistance. See, in parallel voltage becomes same. So the same voltage appears at the voltage drop across 40 ohms appears at V2, right? V2, the voltage being same, that is which the voltage drop across 40 ohms. So we may write 40 times I2, because this one due to current 2, but there is no current, so this is current I1 actually. But it was the ratio of V2 over I1. So V2 in terms of I1, yes, 40 times I1 over I1. I1 is cancelled with I1 is 40 ohms, right? So Z21 comes out to be 40 ohms. Okay. So we have to for the calculation of Z11 and Z21, for the calculation of Z1 and Z21, we connect voltage source at input terminals. For the calculation of Z22 and Z12, we connect voltage source at output terminals and letting input terminals open circuit, right? So for the for the calculation of Z12, what was it? It was a ratio of V1 over I2. This time I2 current flows because source is connected on secondary side, but I1 is equals to 0, but there is voltage on secondary side, right? Sorry, primary side, V1, that is primary side, input terminals. So for Z1 to Z22, we apply voltage source V2, we apply voltage source V2 to the output and leave the input is open circuit. So Z12 becomes V1 over I2. As we know, it was a ratio of V1 I2. What was V1? V1 voltage is nothing but the resistance time this current. So this is 40 times I2, 40 times I2, because I1 not flows, I1 0 because open circuit, I2 flows. So 40 times I2 over I2. I2 is cancelled with I2, so Z12 equals 40 ohms. Similarly, Z22, Z22 impedance equals to, it was a ratio of V2 over I2. So what is V2 in this case? This voltage, see, this voltage equals to this drop plus this drop, Kirchhoff voltage law. This voltage equals to this drop plus this drop. So we have basically 30 and 40 are in series. So 30 plus 40 both are in series times I2 over I2. I2 is cancelled with I2. So Z22 equals 70 ohms. So we may write in the impedance matrix form. The impedance matrix form Z equals Z11, Z12, Z21, Z22. Right? So Z equals 60 ohms, 60 ohms, 40 ohms, 40 ohms, and 70 ohms. See, Z12 and Z21 are equal. Okay, I hope you understand.